I want to thank the organizers for the invitation to come here. It's always a beautiful drive down from Palo Alto. And if you read the title, you notice that it was longer. This was when Andre did not disclose the very limited time that we are all allocated for the talks. So I chopped. Sorry? I paid. You got the check, you cashed the check, but I don't get more time. Anyway, so I just want to talk about something I never talked about before. This is more recent work that we are still thinking about. I'm going to show you results. It's in the spirit of the talk that Kamran Benya gave. He's always my mentor for thermal transport. It's going to be at a very basic level. We are going back, I don't know, 150 years at least. And most of this work was done by Eric, started by JC, and people who are thinking hard now about the problem are there. So the part that I didn't talk about, I'm just flashing it, so it will be recorded, but I just want to talk now about this thermal transport through a CDW transition, a variety of transitions. And I have to start from the beginning, some pedagogy. So we start from the entropy density and the associated current density, where we have two conserved quantities, the energy and the number of particles, or if you want, the charge, if I want to use instead of just the chemical potential, the electrochemical potential. Then I get, from there I get the two coupled Onsager equations. And again, if mu is the electrochemical potential, then this simply relate thermoelectric effects to thermal effects. Okay, so that's very simple. If you take some limiting cases, take for example no heat current, there's no temperature gradient, then you get Ohm's law. And Ohm's law, you can work it out. It's the current density is proportional to the electric field, which is the gradient of the potential, which if you just work out this derivative, you get out of it the famous Einstein relation that the conductivity is proportional to the diffusivity of the electric charge. Similarly, if you put current, no convection, only thermal current, you get Fourier's law, and there you have that the heat current is proportional to the gradient of 1 over T as it is written in the Onsager relation, so simply the gradient T, and the proportionality constant is the thermal conductivity of the material. Okay, this also leads to another Einstein relation, which is the thermal conductivity is the heat diffusivity times the specific heat. Okay, and from there, when you have these two Einstein relations, you get the Wiedemann-Franz. Simply divide the two, and if the two diffusivities are indeed equal, when only electrons are at play, then you get the Wiedemann-Franz law, and L, the proportionality constant to the temperature, is simply the Lorentz number. Okay, so far this is very simple. When we do experiments in the lab, and this is very important, we usually work at constant pressure. And let me just mention that at least within free electron approximation, constant pressure versus constant volume, or constant chemical potential versus constant number, all these differences, as well as the addition of electrochemical, the thermoelectric part, they are all adding terms of order T over T Fermi square, so we usually ignore them. And we end up with a simple thermal diffusion equation that we usually try to solve by looking at the temperature as a function of position and time. Okay. Now, important for my discussion today is that you can write this also in terms of components, and especially if you ignore this term, it's usually not important. You get this equation where this is the thermal conductivity tensor. Okay, so if you have an anisotropic material, then you have thermal conductivity different in different directions, just like you have for the electrical conductivity. So from here, it immediately defines a diffusivity tensor, which is the thermal conductivity tensor divided by the specific heat. Now, the important thing here is, and the way I wrote it, is that if I now take the thermal conductivity and I divide it by the specific heat times the diffusivity, I get 1. And this is now independent of what carries the heat. I don't know. I mean, in fact, this type of relation was invented before people knew what carries the heat. If there are electrons or phonons or whatever, the people didn't even know about that. So it's really, heat is a thermodynamic fluid, a hydrodynamic fluid, okay? And so you can consider this kind of like a Wilson ratio, okay? You test how well this hydrodynamic fluid of heat behaves by testing this ratio. And this is what I'm going to test now as I go through some phase transitions, in particular today, CDW transitions, okay? Now, when you are talking about metals, where people usually like to look at failure of for example, Wiedemann-Franz, this is a few levels more fundamental than the Wiedemann-Franz, okay? You first want to make sure that heat flow is really obeying thermodynamics, then you can also check for Wiedemann-Franz, okay? So, of course, since I'm going to talk about phase transition, I need to talk about critical phenomena in the vicinity of the phase transition. So there is a Bible for that. That's the Hohenberg-Halperin Reviews of Modern Physics. And depending on conserved quantities, you can find which of the models should fit your problem. And then, I mean, for example, if the thermal conductivity is constant through the transition, then you are within model B. There are no for model B, there are no unconserved, non-conserved quantities, and critical behavior is given as such. I'll come back to that. Okay? So, since time is short, let me just go for the results. So let me start with BISCO, bismuth strontium calcium copper oxide. This material has a charge order, which you can see it here at low temperature. It's almost checkerboard-like. That's from our STM work from a zillion years ago. So there is a charge order, but it's kind of a crossover. It's not a well-defined phase transition in all the experiment. Here are measurements that we did on BISCO crystals of thermal diffusivity. Oh, I should mention. So it's a very interesting effect that physicists, I mean, I'm talking about a ratio of 3 quantities: thermal conductivity, thermal diffusivity, and specific heat. Physicists like to measure thermal conductivity and specific heat. Typically in all, throughout the temperature range. On the other hand, engineers like to measure thermal diffusivity and specific heat, because thermal diffusivity and specific heat, both you can put in some purchased instrument. Diffusivity is basically you put a heat pulse. I mean, you take a big sample, you put a heat pulse, you measure how long it took for the heat pulse to arrive, you get diffusivity, okay? But if you try to look at physicists' papers, try to find all three quantities, good luck. They are usually not measured. So, of course, what I'm going to show today is that we did measure all three quantities. So here is BISCO, that's the diffusivity. Here's another one where we take the diffusivity just in the low temperature regime, multiply it by the specific heat. We didn't measure specific heat for that particular crystal, others we did. You see that they kind of match very nicely. That's the specific heat that we took. It's similar to other specific heats of BISCO that people measure. Thermal conductivity of BISCO was also measured by Foro in this paper of Allen et al. It turns that the thermal conductivity as derived from here, they all agree. And in fact, if you look at the ratio, that's from, this is basically taking our thermal diffusivity and the thermal conductivity of this Allen et al. This is our measurements altogether. And you see that this is 1, and it's basically around 1. Remember, thermal conductivity is a little bit more difficult to determine exactly because you need the geometry of the sample in order to multiply whatever heat. Which material is this? Sorry? Which material is this? BISCO. I'm still within BISCO. Okay? All right. Let's talk about
electrons and phonons?
Everything. I don't know what's inside. That's my point. And it's very interesting also to note that the Einstein relation tells you that you divide the thermal conductivity by the total specific heat. And the specific heat is all the density of states of everything, including, for example, bands that don't disperse, and therefore they don't conduct entropy. Nevertheless, they all appear together in the Einstein relation, and it works. Let me show you now, I added that because it was introduced by Steve Wilson, the CVS, as we call it, Kagome system, okay? You remember there is a CDW transition, first order, very important transition at 94 Kelvin. That's resistivity, this is the susceptibility, you all saw it on Monday, and the specific heat shows this huge anomaly. In fact, here this anomaly from two other groups, other papers, all very, very sharp anomaly. Thermal conductivity was measured again by yet another group. And you can see that there is actually nothing. That's the thermal conductivity derived from the resistivity, okay, using Wiedemann-Franz. But let's drop that. We are only looking at what was measured. That's the thermal conductivity. There is nothing here, okay? So, but thermal diffusivity was not measured. Okay, so here are our measurements. That's the specific heat. Again, you see how sharp it is. This is the resistivity. The derivative is very sharp. And this is the thermal conductivity. And this is I thought the music should be at 1:30.
This is a spam call. It's a spam call. There is nothing you can do about it.
and that's the thermal conductivity. And just to make the point, in my opinion, one of the best experiments that showed that indeed this is a first order transition, it's the NMR, in which a single vanadium NMR site was split, and the split width is 2 Kelvin, which is the same width as the anomaly in the specific heat, or the anomaly in the derivative of the resistivity. That's the thermal conductivity. Again, you see there is no anomaly like that through the transition. Nevertheless, this is the thermal diffusivity that we measured, okay? It kind of looks like the thermal conductivity, except here in the transition region. Okay, so you take the ratio, and this is the ratio. This is 1, and that's the transition. And it's only 2 Kelvin. Okay, here I magnify just that relation. So for that first order transition, above this ratio is 1, below this ratio is 1. Okay, so you don't see anything in the CDW regime. Okay, right. Okay, again, time is short, so let me move now to the more interesting system. That's erbium tellurium 3. It's one of a family of rare earth tritellurides. And we again measured all three quantities, but this time there are two phase transitions. You can see it here. That's the resistivity. That's the resistivity in the two directions, and then that's the ratio of them. And you can see that where these two transitions are. If you take the derivative of rho c, and rho c is the red one, the t that's here, you see where are the two CDW transitions. Around 260, 262, and then around 160 degrees, okay? In the first transition, that's the C direction, it becomes a 1D CDW, and then at 160, the perpendicular direction adds in, okay? So it turns that you can even intercalate this material with palladium, then superconductivity will appear at above a certain intercalation. But the point is that even with limited small amount of intercalation, still STM work shows that at most what you get from a pure system is basically a Bragg glass, okay? And therefore you can envision that the CDW really has in the pure system long range order and in the maybe slightly intercalated at most power law decay. Okay, again, here are the measurements. This is the specific heat that we measured. The first CDW, which is the important one, is somewhere here. There was no resolution. I'll show you in a minute the specific heat from here. That's the resistivity in the two directions. So from now on, all the C direction, which is the primary CDW direction, is going to be in red, and the perpendicular direction is going to be in blue. That's the thermal diffusivity. Look at this strong anomaly. The fact that we don't see this weak anomaly is still a puzzle if you take the ratio. And this is the thermal conductivity in the two directions. Looks very similar. Again, there is no strong anomaly, okay? And so you can calculate from the thermal diffusivity and specific heat the thermal conductivity associate, as is, and you know, from there you would, for example, conclude that Wiedemann-Franz, for example, fails because this is the electronic one you calculate from the resistivity, so the difference is here, and then at least in the vicinity of the transition, in the critical regime, something very wrong happens. But now that we measure the actual thermal conductivity, here it is. So orange corresponds to red, light blue to dark blue, and you see that, as you put it, the C direction, it looks like it's kind of fits the calculation. As I said, there's always geometrical factors, so small deviations are accepted. In fact, the strong deviation is only in the critical regime. We know, I don't show it here, but we know that this is a mean field type, and you can actually notice here that this really looks like the mean field specific heat. you expect. Again, this would put this in model B. But look at the perpendicular direction. Okay, it's very far from the thermal conductivity derived from diffusivity and specific heat. And so let's now look at the ratio. So this is the ratio, kappa over CD. That's in the primary direction, the C direction. You see that there is anomaly only in the critical regime. But in the perpendicular direction, we have a deviation from the ratio, from the 1, and it continues all the way to the second CDW, where the system becomes more isotropic, and then below that, it goes back towards 1. So there is a regime here in which, in one direction, that ratio is obeyed. In the perpendicular direction, it's not, as if there is a difference in the hydrodynamics in between these two CDWs. So again, as time is running, let me just propose one solution, which is not worked out fully. Actually, there are some more detailed calculations that my theorist friends are working on. But suppose, just like in the case of the thermoelectric effect, and I forget about those, that there is another mode that can diffuse and carry energy. Let's say that the phase mode. And when the system is in the one-dimensional regime in between the two transition, then the system is allowing for that to happen in one direction, and then there's going to be some free energy associated with it. Let's say proportional to the gradient of that phase. There is going to be maybe an Einstein relation, which is going to relate the energy current associated with this phase mode and the gradient of the phase. If such an Einstein relation exists, then you can see from dimensional analysis that if this is a diffusivity and this is the proportionality constant of the current density, then this is going to be a constant which is a bulk modulus per unit length, which starts to make sense when you're talking about the CDW, and maybe even that the stiffness is related to that modulus through some lengths, let's say the length over which the phase changed by, let's say, pi or something like that. So that's just a framework of a first proposal. The one that I strongly believe is happening is that indeed there is another channel in between the two CDWs which carry energy, and therefore when you look at the heat current, you need to take this into account, just like you do when there is a substantial thermoelectric effect, and you have to add it to the equations if you want to balance the heat. But now it is associated with the CDW transition, and for this particular case, it happens in the regime between the two CDW. So this is, I mean, to me, this is real surprise. This is something I've never seen. I mean, I showed you the CVS, with the first order transition. Everything is normal above and below the transition region. Well, there you are really subjected to the time scales of the measurements, in particular diffusivity. Okay, we measure diffusivity between 200 hertz and 30 kilohertz, Okay, so in the critical regime you can have differences, but I expect that everywhere else this ratio is going to be 1, but this is not obeyed here between the two CDW transitions, which to me is a big surprise. So thank you.
So thank you very much. Oh yeah, that's.
As you showed in the beginning, right?
Yeah.
This is really a tensor relation.
Yes.
So if you were to measure this along a known principal axis, then there's no reason to be satisfied. I'm just wondering whether there could be a more mundane explanation that maybe the CDW is breaking more symmetries than just that, so you're not measuring one of the principal axes.
Well, so the way we determine the principal axis, besides using X-rays that our friends do and tell us these are the directions, and we cut the samples, one in the direction, the other in the perpendicular, and that's how we did the thermal conductivity measurements. There you need what we can do with I didn't show you the apparatus and the way we measure thermal diffusivity, but it's basically you have it's a 2 lasers measurement. You have one laser, 1 micron in diameter, hitting periodically at a spot, and then we measure the response at some r distant from it, typically 10 microns or so, and we go around. So we go around and we find what where is we actually see all the oscillations when there is anisotropy, and that's what determines the principal axis. And in all cases, that includes all the cuprates where we did, for example, YBCO is very anisotropic because of the chains. They coincide with the principal axis.
Hi, Aaron. Very pretty stuff. I have a question. I think something went by so quickly I missed it. So I get that in the case of a second order transition and critical fluctuations, I understand what you're saying, but for the vanadate, you implied that it was a first order phase transition, and yes, you still see an anomaly. So
no, so the anomaly in the, first of all, there is a 2-phase regime, and in that, my point there was that I see the anomaly only in that two-phase regime. That's where I compared it. I compared the widths to the NMR. Okay, I expect it there because when you have 2-phase regime, then dynamical measurements depend on the time scale of the measurement. Usually specific heat and thermal conductivity are quasi-static.
Right. Okay.
Thermal diffusivity is not. You measure it at a finite frequency. And indeed, in fact, even the specific heat, if you look at different groups, the peak is different in size depending on the method by which people measure. So that's what you expect in first order transition.
So it's not so much that it's necessarily critical fluctuations. It's just that you need in the mixed phase regime. You can also have the time dependent.
Of course.
Okay.
Of course.
Aharon, as far as I understand, so you find and you think that the sliding modes of the charge density wave play a role in heat transport, but usually they are rather sensitive to disorder, to pinning, and so on. But the temperature is rather high. So is this why?
Yeah. So that's why through this talk I mentioned also that even when you introduce disorder, and we usually introduce disorder in this material through intercalation, light intercalation, at most you get a Bragg glass. So correlations decay algebraically. For the pure system, in STM, we measure hundreds of angstroms of really beautiful, so basically, I believe that from that point of view, the system is pure for the CDW.
Okay, I see.
Hi, I want to ask, maybe I have missed it, but if it's because of electric thermal effect, should it also affect the charge channel and show that like charge conductivity divided by.
The measurement is only thermal measurement, and I stated at the beginning that this is a very high carrier density material, and there is no reason, and measurements of thermoelectric effect in this material give you a typical small number of order of 1 to 2 microvolt per Kelvin at low temperatures. It's small. There is no reason to believe that thermoelectric effects are going to interfere with that. So I don't need to look at the charge part.
Aharon? Yeah. Here, me.
Yeah.
Me. A couple of quick questions. So the physics is classical, right?
Yeah.
Physics is classical, right?
Yes.
The part that you understand. The
Yes.
part that you don't understand, we don't know what's going on.
Yes.
Just wanted to make sure. Second, how do you know in the hydrodynamic thermal transport regime? I mean, that's not easy to settle, that you're in the hydrodynamic regime. Maybe
So
you're not.
that's my test for the hydrodynamic regime is kappa over CD is 1.
Okay, that's what it is.
That's the test.
And the last question is that, of course, Wiedemann Franz, which is, I agree with you,
Yeah.
Not as deep as what you're using, that of course fails whenever you have inelastic scattering. It's really inelastic. Does that feature show up in this inequality, which I have not thought about this equality at all?
So you see the problem when you have transport by both electrons and phonons is to determine how whether Wiedemann Franz fails or not. And you cannot do it in the longitudinal direction because there is a phonon channel in a normal case, phonon channel and the electron channel, and so you calculate the conductivity. I mean, like where was it? No, here. Okay, so forget about the critical regime. You calculate the conductivity, the thermal conductivity based on resistivity. Okay, that's the Wiedemann Franz, and you then subtract it from the measured thermal conductivity, and you get something that is very typical for this kind of material. So you say, oh, it works. Yes. The problem is that otherwise you don't know. So what people usually do, and it started to be, people started to do it in the cuprate, for the cuprates, is that under some assumptions, the transverse thermal currents should obey the same Wiedemann Franz. So the idea is if you measure the thermal Hall effect and you measure the Hall effect that is transport in the transverse direction, phonons will not be part of it, and the ratio will give you the correct Wiedemann Franz. But otherwise, it's very difficult to say whether Wiedemann Franz works or not.
Aharon, about the same slide. Both diffusivity and conductivity show features at the two transitions. Specific heat does not. Is there understanding?
So, okay, so actually the specific heat does, but the...
No, not at this example. It's the last example.
I know.
Uh-huh.
Am I going? Oh, sorry. I have it somewhere. I have... yeah, here. So it was that. So the specific heat anomaly is very difficult to measure. It was for this material, the erbium telluride. It was measured by the group of Munso.
But it's extremely tiny.
Sorry?
It's extremely tiny.
So it is tiny because it is in the Dulong-Petit regime, so it's very difficult to extract it. But otherwise, it's 2 joule per mole Kelvin is not that small.
No, but I mean it's more simple. You have a ratio of 3 quantities.
Right.
2 of them show clearly seen features as a transition. The third does not.
Yeah.
And I'm wondering, does it mean that there should be some cancellation of the features between 2 and the third one is out?
Yeah. So in principle, I didn't want to get into that because this is kind of, in principle, I shouldn't care what's inside. The ratio should have been obeyed, and if the thermal conductivity is featureless through the transition, then I should get 1 over the specific heat. Okay, we don't see that. We see a very strong effect in the diffusivity, but we don't understand. But if you assume, which is actually I find interesting, if you assume, that's the anomaly which you don't see in the specific heat. But if you assume that Fischer-Lange works, and you take the derivative of the resistivity, and say that the anomaly in the resistivity is the specific heat, look at that. It's exactly matching the anomaly in the diffusivity. So there is an issue of time scale in measurements, but this issue in the critical regime, but I don't think it can explain to me the biggest anomaly, which is what happens in between the two phase transitions. Yeah. The transition is actually not, it's a second, these are second order transitions. Yeah, so, these are second order transitions.
Yeah. So I think we can.
Thanks, really interesting. Just from an experimental point of view, can you comment maybe in your diffusivity microscope on what is the rough magnitude of the temperature gradients and the temperature changes, and is there any possibility that some of this is a non-linear effect?
Yeah, so we do check for linearity by changing the power of the heating laser, and everything here is in that linear regime. So that's not an issue. Okay. The typical temperature gradient that we have in this temperature range, as we estimated it, I think it's about 0.1 Kelvin over a length of 10 to 15 micron.
Oh, 0.1 Kelvin. Okay, thanks.
Less than, but I cannot.
Yeah, okay. Actually, I have a related question. You wrote heat transport equation early in your talk.
Yes.
Page 2 or something like that.
Maybe.
And in that equation, there was a nonlinear term proportional to grad T squared.
Right.
And the question is, how big is this term practically compared to diffusivity term, and can you actually make it big?
So,
because if it is big, then this will
excellent point.
Super interesting equation.
Yeah. So which is related to what Philip asked, and we believe it's very small, as I said. So that's why I didn't introduce it back. But yeah.
Can you make it big?
Yes. Yeah, we can.
Good.
So, Aaron, just to be sure,
yes.
It is a comment about, Andre's question, just to be sure that we agree about this. Thermal conductivity, you can separate it to electron and phonon component. Specifically, you can separate it for electron and phonon component. Exactly because diffusivity in the conventional case is the ratio of the two, yeah. you cannot talk about diffusivity of electrons and phonons separately.
Yes.
So what's happening in this system, it's not a mystery. The jump in specific heat is very small. The jump in thermal conductivity is more important. It is just because there is a lot of entropy which is phononic,
yeah.
but mobile entropy is mostly due to electrons. So this is why you have a big anomaly in thermal diffusivity, because when you have this phase transition, a lot of things happens to thermal conductivity of electrons, but compared to specific heat of phonons, this is very tiny.
Yeah.
So up to here we understand. So we don't understand why it doesn't become one. Do you agree with this?
So I basically answered it exactly what you said in a different way by looking at the derivative of the resistivity, which is all electronic, assuming Fischer-Lange, then this would be just the electronic portion. But at the same time, I still would expect that if I have all these components, I will get one, and I don't. So there is, but again, this is within the critical dynamics, and there are different time scales. My main puzzle is beyond the critical dynamics of the phase transition. It's here. I mean, this is really, really puzzling.
Okay. So I think we thank the speaker.